today I'm going to go through a series of questions that deal with the motor effect. How well do you know the motor effect? So I'm going to go through a whole bunch of questions, mainly multiple choice, though there is one short answer question. And as I go through each question, pause the video, have a go at answering the question, and then I will go through the answer. So let's start. The diagram here shows a magnet standing on the bottom of a dish filled with a conducting solution, a copper wire suspended freely from a point above the magnet with its tip in the conduction solution. It is held in the position shown. The switch is closed and the wire is released. Which of the following will be observed? Is it A, the wire will rotate about the magnet, B, the wire will be attracted to the magnet, C, the magnet will rotate about the vertical axis, or D, the solution in the dish will rotate about the magnet? Pause now. So let's go through the answer. Now, when you look at a question like this, it's important to read the question really carefully, and that includes the diagram. So don't just go read it and go through the answers. Have a close look at the diagram. And so let's look at the features here. Okay, so we've got a switch here, and the switch is going to be closed. And really important here is the fact that we've got a DC supply here. And in this case, the large line suggests that the current is going to go up, and therefore it's going to go down, and therefore in that direction. So we know that aspect there. The next thing we know is we have a magnet here, and the magnet of course has a magnetic field around it, and a magnetic field will be such that it goes around the magnet like so. Now what's missing? Of course the direction. And so here is my lines, and that shows the direction. So the question of course is, what will happen here? Well, this wire here will be in this magnetic field and therefore will experience a force. That's the motor effect. Now, the fact is that as these magnetic field lines go and stretch out this way, we are not interested in any part of the magnetic field lines that are parallel to the wire, because that will not experience a force. The rule is that the magnetic field lines need to be perpendicular. So we're interested in the magnetic field lines that are perpendicular to the wire. We've got a magnetic field that is, in this case, heading in that direction. We have a current with which we've already established is in that direction. And so using your right hand palm rule, that basically means that it will experience a force, in this case, into the page. So there is to be a force, and if we do it across, it'll be into the page, which means it will go that way. But of course, this is a three-dimensional image, so it's going to go around the magnet. Clearly, A is the only possible answer. So the answer is A. Question 2. Current carrying wire is placed perpendicular to a magnetic field. Which graph correctly shows the relationship between the magnetic field strength B and the current I if the force is to remain constant? Pause now. Okay, so this is all about, of course, the motor effect. And the motor effect, the current carrying wire will experience a force in a magnetic field, and the value of the force is equal to BIL sine theta. That's the formula. Which graph represents this formula in the conditions provided? Well, first of all, we know that the force has to remain constant, and we're interested in the relationship between B and I. So if we wanted to show the relationship between B and I, we need to rearrange this equation. And so we get B is equal to F over IL sine theta. Now, we're already told it's perpendicular, so we can remove this one over here. Secondly, it's a single wire, so we know that this is already constant over here. We know also the force has to remain constant, so we can leave that as a constant as well. So what we end up getting is that B is proportional to 1 over I. In other words, they're inversely proportional to each other. The only graph that represents this is C. Next question. A current carrying wire passes through a region of uniform magnetic field, magnitude 0.05 Tesla, and a result experiences a force of a magnitude 0.03 newtons. What is the current? Pause now. Now this is a really interesting question. A lot of students struggled with this question because they think, okay, F is equal to BIL sine theta, and that theta must be the 30 degrees. But no, that theta represents the angle between the wire and the magnetic field lines. And if you look very carefully, this wire is still 90 degrees with the magnetic field lines. So why is this angle important? Well, we need to know the length of the wire in the magnetic field, but we're only given this distance over here. So we can work out this distance using simple trigonometry. So in other words, the sine of the angle is equal to the opposite, which is 0.2, divided by the length we're interested in. So if I rearrange that, I get the length is equal to 0.2 divided by the sine. In this case, it's sine 30. So we also know, of course, that F equals BIL sine theta. So if we go F is equal to BIL sine theta. Now I'm going to remove the sine theta because sine theta is 1 in this case. So I've got F, and F of course is 0.03. B is 0.05. The current is equal to, well, that's what we're going to look for. The current is I. And the last thing is the length, and this time we know it's 0.2 over sine 30. Now, what is sine 30? Sine 30 is a half, so 0.2 divided by half becomes 0.4, so this answer here becomes 0.4. So I ends up equaling 0.03 divided by 0.05 multiplied by 0.4. And if you look very carefully, that's equal to 0.03. That ends up being 0.02, and therefore that equals 1.5 amps, and hey presto, A is my answer. Let's have a look at this question. And in this case, we're looking at the motor effect of a situation where we have two current-bearing wires and they will exert forces on each other. Pause now. So let's have a look at it. Alright, so the first thing is we understand that Q and R are opposing directions. So Q is going to apply a force on R. It is going to be a repulsive force because they're in opposite directions, and that is going to be equal to F newtons. So we know that already. Now the thing is though, the force due to P is clearly going to be smaller than the force due to Q. And why is that? Well, it's because it's twice as far as that. So the force due to P is going to only be equal to half of the force that R is going to experience due to Q. So we already know that. So that's going to be F over 2. But the question is, what direction is that going to be? Well, in this case, P is in the same direction in terms of current as R. So that's going to provide us a force in that direction, but we've already established that force is only a half because it's twice as far. So the net force ends up being clearly Fn is equal to the F value, F newtons, minus the F over 2, which gives us a total of F over 2 newtons. Which direction? Well, since this one is still larger, it is towards the right, giving us the only possible answer, B. Next question deals with understanding how a galvanometer works. Components of a galvanometer are shown. What is the purpose of the spring in the galvanometer? Is it to ensure a uniform force on the coil, to complete the circuit through the coil, to counteract the motor effect, or to increase the magnetic flux through the coil? Pause now. So let's have a look what this is happening. Well, of course, the galvanometer works on the principle that F is equal to BIL sine theta. That is, it's all about the motor effect. But what we want is that we want the situation here. This is also about torque. And so torque is equal to BAIN because this rotates as well, cosine theta. So there's the motor effect, and there is the motor effect in a rotational situation. Now, for this to be a good galvanometer, we need torque that is applied to this situation to be directly proportional to the current. This is what we want. We want torque to be proportional to the current so that the needle moves and stops whenever the current is adjusted. So if the current is doubled, the needle moves twice as far. Well, in order for this to be happening, then BAN and cosine theta all have to be constant and unchanging. Well, that's true for that. The area of the loop is constant as well. The number of turns is constant. These are all part of the structural features of our galvanometer. And finally, the fact that we've got a curved magnet ensures that the magnetic field lines are always parallel to the loop of the actual motor. So that remains a value of 1. So basically, we now get torque is equal to some sort of constant multiplied by the current. That's fine. But if we apply a torque and a current, what's going to happen? It's going to continue experiencing force and it's going to continue to move. So what we want to happen is a spring of some sort that will change its tension as the torque increases. And that's in essence what this spring does. As this thing starts to turn here, the spring starts to tighten and the spring actually stops the coil from turning when the force due to the spring is equal to the force due to the actual turning. And let's say we'll call that the force due to the galvanometer. And then it will stop. Now, if the torque actually increases due to the increase in current, then what's going to happen is this value here increases, but then as it stretches the spring, this value will also increase until such time they equal, so it stops it. And that's the essence of the spring. So, is it to ensure a uniform force on the coil? No, definitely not. Is it to complete the circuit through the coil? The spring has got nothing to do with the coil. So no, that's not the right answer. Is it to counteract the motor effect of the coil? Yes, it is. To increase the magnetic flux through the coil? Again, that's nothing to do with this question. So the answer clearly is C. Next question. So here we have again a situation of a loop of wire in a magnetic field. Now, what is happening in this situation? Okay, let's have a look at it. An electric motor is set up as shown. When current is applied, the coil does not turn. Which of the following is required for the coil to start turning? Is it A, the magnetic field must be increased? Is it B, the direction of the current must be reversed? C, the magnitude of the current must be increased? Or D, the starting position of the coil must be changed? Pause now. So let's have a look at this situation. Now again, torque is equal to BAIN cosine theta. And that cosine theta is the angle between the magnetic field lines and the plane of the loop. In this case, they are right angles to each other. In other words, in this case, my theta is equal to 90, which means over here, I'm going to get a torque of cos 90, and that's going to equal 0, which is the reason why it's not turning. And ultimately, from a physics point of view, it's because, if I try to draw it, is that the forces that are exerted here, the current is going up over here, so the current is going up, that is going to experience a force towards the center like this, and in this case that force is going to apply, that current is coming down, and therefore the force that is going to be exerted on that aspect there is towards the center over here, and therefore you're not getting a tangential force, and therefore you're not going to get a torque. So how are you going to get this to turn? Well, you can't do it by increasing B, you can't do it by changing A, you can't do it by any of these variables over here. You can only deal with the angle. Once the angle changes, you're going to get some component of the force here that is going to actually be at a tangent to the rotation of this situation. And that's what you want. You want a force that is at a tangent. And so, no, not changing the magnetic field, not changing the current, not changing the size of the current, only the starting position will affect it. The diagram shows a DC motor with a constant current flowing to the rotor. Which pairs of graphs best describe the behavior of the force F on wire AB and the torque on the rotor as a function of time? Pause now. So this question is a little bit more complex in terms of the motor effect, and in this case what we have here is a DC motor. And so we need to again analyze this question really carefully. So first of all, we've got a DC supply which is causing the current to head in that direction. And of course the current reverses on that side in that direction like so. What does that do? Well, that's going to apply a force, and if you know that the magnetic field lines are going to run across that way, you can clearly see that there's going to be an experience of force down on this side and up this side. Now, as this starts to rotate, that force and that force remain going up until such time when this loop ends up down the bottom. So when we've got AB down the bottom over here, it's going to momentarily switch off because the commutator comes into play over here. And AB will be on the other side. Now AB will receive a current going in this direction. So the current flips direction, but for all intents and purposes, the current is constant until it flips the reverse direction on the other side, which means the force remains constant throughout until it flips completely to the other side. That automatically removes this one and this one. So now we are down to two possible answers. And if you are completely stuck about understanding torque, you at least now have a 50-50 chance of getting it correct. But the important thing now is what is happening to the torque. Well, as this turns, then the amount of torque actually decreases. Let me explain it to you this way. So imagine I've got my loop here and I'm just going to use a yellow line. So my yellow line is over here, and this is AB over this side, and this is the other side over here. And my force in this case is going to be down on this side and up on this side. And you can clearly see that's going to be that position over here. Now, if I were to then draw this at a later stage, like so, and again, this is AB where it's two-dimensional over here, and in this case, the force is still down and this force is still up. But what we want is actually the tangential aspect of it. Only this component causes the turn. This component does nothing whatsoever, so it gets weaker. And if I continue that process along to a really sharp angle over here, you can clearly see this is the force still acting down. It hasn't changed at all. We haven't switched it yet through the commutator. But in this case, again, the amount that is actually going that way, which is tangential to the rotation, is significantly less than we had here and certainly over here. So it gets weaker. But of course, as soon as it gets to beyond the vertical, it switches direction and it starts to increase again, and it continues to turn in an anti-clockwise direction, which means the only possible answer is this one over here. You can see over here, it is starting at a maximum, it ends up at 0, and then increases again and goes through. The torque does not remain constant, therefore the answer is B. This question is a much more difficult question, and it really tests your understanding of the angles involved in the motor effect, and in particular in terms of a DC motor. So let's have a look at it. The diagram shows a single loop motor, and the equations torque equals NBIA cos theta and F equals BR sine omega can be used to calculate the torque in the motor and the force on the length of wire WX respectively. What angles are represented by theta and omega in the above equations? Give you a moment to answer the question. All right, so let's have a look at the situation. All right, now we can see that the plane of this loop here is not parallel to the magnetic field lines. So the magnetic field lines, if you look at the diagram over here, magnetic field lines are running in that direction. But my plane clearly not parallel to it. In fact, it's been moved 30 degrees. So that relates to torque is equal to BAIN. That's how I always like to write it. Cos theta. That's the formula. But in this case, that's my theta over here. Now, they're using the symbol theta here for that formula, which is nice for us. And so therefore, it's pretty clear that 30 is going to be the angle here. That's 30. So if we go down the page, that means we've got this answer and we've got this answer that is possible for this. But what about the other angle? Well, first of all, what is the formula? F is equal to BIL sine theta. And what is theta? Theta is the angle between the wire and the magnetic field lines. So X and Y are rotating, but if you look very carefully, even though this loop rotates, X and to Y never changes the angle with respect to the magnetic field lines. It always remains perpendicular. So therefore theta has to be 90 degrees. But of course we're using omega, so omega is 90 degrees. That means it's that answer and that answer. The only possible combination that fully explains this is A. And there's your answer. Now we go to a more difficult question to deal with two wires that exert forces on each other due to the fact that they both carry currents. But this particular question requires some mathematical skills as well. And it's not just about the motor effect. So I'll give you time to pause and read the question carefully and attempt it, and then continue on as you find the answer. So let's have a look at this question. And we need to interpret this question very carefully. We're told that we've got two wires, and you can clearly see here and here that they are in opposite directions. So if a current is applied to this situation, then this force that is going to be experienced will be pushed down. Now this is the reading in terms of mass, and that's given by the fact that we've got a symbol of G, grams, of 12.6250. And so when the current goes on, we expect this reading to increase. So if you're completely stuck and you have no idea what to do from here on in, you could already remove a couple of answers here. So D, therefore, doesn't allow for the big answer. So D is wrong. And secondly, A is wrong because it's the same number. So now you have a 50-50 chance of getting this correct. But don't guess. Let's go through it and what happens. Well, the first thing you need to understand is that this scale is reading in grams, but it's actually responding to weight. So therefore, what we need to do is we need to work out the increase in force, but then convert that force into a comparative reading in terms of grams. And we do that by dividing it by the acceleration due to gravity. So first of all, we need to work out the force that is exerted, and that's equal to force is equal to K I1 I2 it's over per unit length over D. Now, we're told it's 1 meter, so all of a sudden we now can forget the 1. So we've got 2 by 10 to the power of -7. We've got a current is going to be 10 amps, and it's the same value. So therefore we can go 10 by 10. And the distance, of course, is 2 millimeters, and that becomes 2 by 10 to the power of -3. And if we do the calculation over here, we get 2 by 10 to the power of -5 over 2 by 10 to the power of -3. And that gives me a grand total of 10 by 10 to the -2, or 0.01 newtons. But remember, this is newtons. So what we now need to do is get that equivalence in terms of the grams. And so what we get is we've got to go to 0.01 and we divide that by 9.8. And when you do that, we get 0.00102. But that's kilograms. So therefore we get 1.02 grams. Now, if you look over here, you can see that we have a reading already over of 12.6250. We have to now add our 1.02 grams that we have over here, giving us 13.6454 grams. So the answer is C. And our final question is not a multiple choice. In this question, what we have here is a model of a motor that a student designed, and you have to identify 3 mistakes that the student made in designing this. Pause now, see if you can identify the 3 mistakes. So what are the 3 mistakes? Well, the first thing to understand is that we need a motor here that has a coil and it needs to be connected to the commutator. So that's pretty easy. Number one, there is no connection to the commutator. So that's the first easy one. What's our second mistake? Well, the second thing is when you've got this coiling around here, it must remain in the same direction on the other side. And if you look very carefully here, this wire is now going in the reverse direction. So any force that is applied on one side here will be counteracted by the wrong force on the other side. So number two, the windings need to be consistent. That's clearly the second mistake. But what's the third mistake? Well, the third mistake is actually the orientation. You see, if you look at this situation over here, even if the windings were correct, then what is happening here is that the current is going in this direction over here. It's going that way over here, let's say, and the magnetic field lines are going in this direction over here. There's my north and there's my south, so they're going in that direction over there. And that means this here will experience a force in the upward direction, but down the bottom it will experience a force in the opposite direction. So in other words, they counteract. So nothing's going to happen in this situation. And the same is true for this side over here and this side over here. So what is the solution? So if I were to reorientate this like so, now all of a sudden, for the commutator to be in this position, all of a sudden now I have the ability to get a maximum torque. So again, if the current is going, let's say, in that direction over here, then that will experience a force in the downward direction like so. The other side will experience a force in the upward direction. Now remember, we're assuming that the windings have to remain in the same direction. So let's ignore the fact that this is a problem. Let's say we fixed it. And the same thing will therefore be true over here. You'll get the force down here and the force up that way. In other words, in the old position, you needed the commutator to be in the off position. In this position, by switching the whole rotor 90 degrees and keeping the commutator where it is, it actually works. So problem number 3 is the 90 degrees out between the commutator and the rotor. In the old position, in that one, it won't turn. But if you leave it in this position, having fixed up the other problems, it will turn. I hope that gives you a better understanding of the motor effect. Thanks for watching. Bye for now. I hope you found that video useful. And remember, like, share and subscribe. Oh, and if you have a comment or a question, or you'd like a concept for me to explain to you, please drop a comment down below. I'm Paul from High School Physics Explained. Bye for now.